Assalamu alaikum. Welcome to Turkish Engineering. In our Thermodynamics II series, actually we have two types of explanation. We have a classical, like hand solution based playlist, and I created another playlist for just using Python and Coolprop or Refprop libraries, which are like thermodynamic property libraries. Using those libraries, I will follow the same questions mostly. I will follow the same questions and solve it by software. Okay, so, and also the powerful thing when you use the software, you can also parametrically change, like see the effect of changing some parameters. Okay, and actually we will be solving a question like from Yunus Çengel's book. 9th chapter, gas power cycles. We have question 13, which we already solved by hand solution, and question 14, which is related to optimization of this. Question 14 says when you change this temperature, only this temperature, they are given like black colored properties are already given at the beginning of the problem. Okay, so when you change your it is like actually before the expansion, right? Before isentropic expansion, and it's constant heat addition. Okay, after your combustion, basically in an engine, if you make your combustion chamber, like you design that chamber which resists high temperatures, let's say more than 2000 kelvins, what will happen? Will you increase the thermal efficiency? Actually, it is well known in the like engine design that more high the temperature, higher the efficiency. But we have some limitations for the materials, right? Some other things, so we cannot exceed some temperatures. But we know that more the temperature, more the efficiency for gas power cycles. So we can see this effect by software, and we will do this. Okay, I already finished the coding, but I will follow two codes actually for question 13 and 14. To show you how you use Coolprop and how you get the values. Okay, we have Jupyter notebook, and where you can just step by step run your code. You can run your code actually by shift plus enter at the same time. You run the selected cell, or you can run all cells. When you run all cells, it just take you to down and just give you the result. But we will follow step by step and see how you use thermodynamic library in Python to solve thermodynamic problems. Okay, let's go back again to problem. We have a power cycle. Okay, and we start by isentropic compression, and then we have some input values. Okay, so we start by using our inputs, defining the fluid. Okay, you are importing the libraries at the beginning, then you define the fluid type. It can be water, air, nitrogen, or anything. So initial pressure you define as Pascal. Okay, E3 means like 10 to the power 3. Okay, because it's kilopascal. 100 kilopascal, you convert it to Pascal by this. Okay, initial temperature, we define it. Second pressure, temperature at state 3, and pressure at 4. Okay, then by using the Coolprop library, just like setting a variable. Okay, you define a new variable, and you set it to a function which comes from which you call it from CP library, Coolprop library. But you just instead of writing this here, for example, okay, instead of writing this long thing, you define it as CP. So instead of Coolprop .Coolprop, we use only CP. It's enough. Then we call for a function which is props SI. So that means properties with SI units. Okay, there are some other like libraries. You can check Coolprop's website to see which kind of functions you can use. So basically we will use always SI unit properties, and this is our purpose. Like what we need from that library is just call the properties. S1, what it basically works with defining two intensive properties, you can calculate all others. Okay, here entropy can be calculated by temperature and pressure input. Okay, you say at the beginning the property that you are gonna calculate entropy, but like per unit mass. Okay, entropy can be like molar entropy or mass-based entropy. So we use mass-based entropy. So you put S mass. Then comma, you have first input. I will use temperature. Okay, as a text you say capital T that understands that you will input a temperature value. So I have T1 already defined. Okay, this is the temperature. And second input as a property is pressure, and you use P1. And the last thing, when you put comma, the last thing you need to give as an input to software is your fluid type. You can just write here air, but instead of like if you have a couple of cycles with different fluids, you can just define it as a variable. It will be easy to use it. Okay, just say fluid. And what happens, you can just only change here to water and see what happens with different like material. Okay, so you say just copy paste this one, and just change here as so you define internal energy, right? And same function, instead of entropy you say U mass. That's all. Okay, that's how you do it. Change it to enthalpy, then you have H mass. You use TP again and fill it as air. You have rho, which is density. You can calculate the density here. And from density, you can calculate the specific volume, right? So specific volume is just 1 over rho. Specific volume is just reverse of the density, meter cube per kilogram. The other is kilogram per meter cube. So just flip it, okay? So then you print the state. You can just state 1 and put all what you calculated here, okay? Then we calculated the properties. Actually, we did it by using the tables, right? Here, actually, entropy is 3.87. When I solved the problem numerically, since I don't have a property database, I fit it to 0, but doesn't matter. Entropy change is important. Entropy value is not important, but change is important. So we will compare the entropy change, what we calculated here, by our hand-based solution, and see if we made it like correct or wrong. Okay. Good thing here, you know S1 just for the isentropic process, you can know the entropy, and you have the temperature from, like actually better to start by this. You know that entropy is equal to S1, second entropy. Then you know entropy and pressure for the second state. Let's see our table. Okay, this is the second state, okay? You have pressure, and entropy is coming from first state. When you calculate first entropy, second entropy is also calculated. So you have entropy plus pressure. And you need what? Temperature. So to calculate this temperature, you say, okay, I need temperature. I will input my pressure. I know it. And I will use as an input my specific entropy. You can say S2. You already defined S2 here, okay? So then, since you know temperature and pressure, now you calculated temperature. No need to put here S. And no need to, for example, at the first step, to calculate temperature, we used entropy. But these actually databases, like thermodynamic databases, will prefer, like you know basically that two intensive property can give me all properties. But temperature and pressure are most powerful properties to call all others. Because at the, like, when you open the box of this kind of databases, how they work with partial differential equations and some modeling, okay, some state equations. So if you give as an input of entropy and pressure, you cannot calculate all range of values. You have sometimes like convergence problem. The solution will not converge. But I actually, when I use this kind of libraries and do some thermodynamic modeling projects, I had this problem. So I troubleshoot what is the problem. So don't use entropy. Don't use like if you get temperature and pressure. If you calculate it, then switch to temperature pressure. Here, basically what I mean here, U mass U2 can be calculated by T and S. Okay, but I know S and pressure as we did it here. But now, if you know temperature, prefer temperature instead of entropy. It's better, okay? So now you define basically all state values, then also specific volume, then you print, okay? That's all. You just now move to state 3. You have constant volume, so you can say that rho 3 is equal to rho 2, okay? And thermodynamic, like this property library or function from this Coolprop, you can use rho, which is density, as an input also. So to find pressure at state 3, we use temperature and density as an input. Then we get pressure 3. Then we go to, okay, density here. Actually, what we can do here is we can switch it to pressure, okay? I'm sorry, not this one. This D mass, instead of temperature and density, we can say we will define it by pressures, and we know pressure 3, okay? But after this line, okay, after I calculate pressure 3, I can say, okay, T and P is enough for me, okay? Let's print. You see that results are same. You can basically use any property, any intensive properties. You have 2 of them. You can calculate the others, but it's better to actually get used to always prefer temperature and pressures, okay? So here, isentropic process, okay, let's take it to as first line. Then here, instead of S3, you can say S4 because you already defined S4, okay? You find the temperature from entropy and pressure. Then by using temperature, pressure, temperature, pressure, temperature, pressure, you can get other properties. And you can print the state values. So now, actually, congratulations, you finished all. You filled the table. What you need, just calculate based on the first law equations. You calculate the heat and work values. Okay. So you basically here you define Q as 0 because of isentropic process. Then change in internal energy, specific internal energy is just U2 minus U1. Then you can calculate work as a function or like from the first law equation. Again, first law, first law, first law. We already did like explanation of hand-based solutions. You can refer to my other video for the Thermodynamics II playlist. But here we focus on how the computational work being designed, or how to basically you can use this software. Then we defined as, you know, that Q input is just a process between 2 and 3. Then Q output is just to fit it to like here is minus if it's less than 0. That means you are converting to Q output as like you are basically taking the absolute value depending on it on that. But okay, but that's not too much important actually. Based on just be sure about the signs. Okay, no need to add this kind of things if you are sure about the signs. And work net, you just add all work values. Then eta, which is your thermal efficiency, can be calculated. You print values. You have the thermal efficiency, which is 48%. We also calculated by hand-based solutions. And you can also plot by okay, most of the times you will need NumPy library to put to divide them as like linear values. From T2 to T3 I have 60 values, so you divide them, and after the, and so you prepare yourself for the to see how the process works. You get a lot of temperatures, right? Because if you don't do these steps, you have only 4 points, right? You have only 4 points. But what about as an array? I have inter values there. How can I calculate it? By using this like NumPy library, you can like calculate for P in P. So this is a for loop, okay? Or like for each for each pressure value between this interval, you calculate the temperature from this function. And for each entropy value, okay, so this is, okay, let's see this one. You do the same idea, but okay, this function, you call it, but you calculate it for all temperature and pressure range. Okay, you have T and P, so that will give you a high range of values. You just use the same idea to get all other properties, as like you are calculating a lot of points. It's 60 points, I think, right? You divide it to 60. Let's say if it's 3, let's change this to 3. You will see that plot will be not that much good. Let's see what will happen. Did you see? You have only 2 points, 3 points, right? 1, 2, 3. So there will be only a line, like straight line then straight line. But the more you increase this, more you get accurate results. Okay, so you take small increments. It's better to get a good visual representation of the graph. We can compare the results. Okay, let's take this. Okay, what's this? This is PV diagram. Okay, what we did is here I have 100, right? 100. It goes to 600. Okay, like this. Then constant until 1840. Okay, 1840. Then you go back to same pressure. So the values are same. I just visually I did not get this kind of like high range. I made like only we have the same values, but the scaling is different. Okay, I did not make an accurate scaling, the same as the software. UCTS diagrams is also the same. Here, the range actually, this range I calculated from the software. S values between these two is same as what we calculated, just 0.92. Okay, so your reference point can be here 3.8 or anything, 3.5, or you can just set it to 0. Not important. What important thing is just a change in entropy. Okay, and temperature values are also correct. What we did here is correct. So basically, this kind of problems you can use Python software or Matlab software or even Excel integrated with the thermodynamic library. And the advantage of using software, let me show here. For question 14, it needs to optimize. It asks you to optimize from 1,500 to 2,500. Take some points. Let's say 10 points. Okay. By NumPy library, we can create this array with like starting point, end point, and number of values. I will just set 10 different temperatures. So define some functions here. Okay, this is like I defined all thermodynamic calculations as a function. Okay, then here T will be okay. Let me show you here. Okay, then since I set them as a function, these are defined functions. Okay, so you can use a for loop. T3 target in T3 values. Okay, and etas is like efficiencies is an empty array now. Empty array, I will fill it. I will, for each, you see, etas append. Append means like just add a new value to your empty array or filled array. Just adding a new value. If you have two, like a vector with 2 values or array with 2 values, you will just be adding a new value, 3, 4, 5. So here actually I will get how many etas I will calculate. based on how much temperatures you have. You have 10 number of temperatures. I will get 10 number of efficiencies I can calculate from like defined function. What actually this code and what we made in here, they are almost same, but instead of using T3, I define T3 as an array with 10 different values, and I use a for loop. Just adding a for loop, not a complicated like programming. You can also get help from ChatGPT to just write this kind of code. So you're just adding a for loop to solve it corresponding to each temperature value. You can calculate the efficiency, then you plot. So this PV and TS diagrams will be calculated for each case. Case 1, when you have 1,500, okay? You go down. Can we expand it? I don't remember how we expand this. Okay, you go down. It's actually for case, second case, you have this temperature, you get another, but they are similar to each other. What we are interested is the efficiency change. Let's see, I have 10, okay. 10 different calculated values. You see your efficiency at the beginning, and hand-based calculation also gave this result. When you keep increasing the temperature to 2,500, you can get like 3% more efficient cycle. But 3% might be less when you hear this amount. Oh, 3% efficiency increase, it's not that much big amount. But imagine that you are running like a huge industrial thermal plant. So increasing just only 0.5% of efficiency make too much money. So this is important. Working with thermodynamics modeling and like parametric based modeling using software enables you to optimize your cycle and design more efficient like cycles or processes or like industrial plants. So this is why we actually try to use and get familiar with this kind of softwares. It can be Excel. I made some videos in Turkish for Excel, using Excel for thermodynamics, but this is a new playlist. We will be following and solving a couple of problems using Python and Coolprop. I hope you enjoyed, and see you at next video. Thank you so much for watching.